Now let's go to memristor, right? We are done with the power device. We have very tight schedule. I give you a feeling. I hope that you can keep paying attention. It's very hot now in your head. Okay, now then finally, let me talk about their different resistive memory. Of course, we don't have time, but if you're interested, read the paper I uploaded. It is a good review. There are different conductive mechanisms. Some are filament type. That is what we have been talking about. You form the filament, right? The vacancy, then you can transport. Some are interfacial, right? And they how then they transport? If they are interfacial, they for this Schottky emission, follow low high tunneling, direct tunneling. Why I want to show this? I want to show you that. That is what we did in the first two lectures. We spent a lot of time to talk about the basics. All these basics are useful now, although I'm not using them here. But if you want to go further, these are all you have learned. But I guess probably you forgot what is Forner-Norheim tunneling. If I were you, I will forget also. No problem, right? But I hope that you know that you can go back to read if you see this issue, this term in the future. FN tunneling. Anyone remember what is FN tunneling? What's the difference between FN and direct tunneling? We only cover in one slide. I don't think you can remember if you did not study. Right. So it is still tunneling, right? Direct tunneling is just saying that the barrier is so thin, then you have the tunneling like this. Forner-Norheim is like field enhanced tunneling. Under high electric field, although you have a thick barrier, but you get the triangular field, right? This is the conduction band, so I can go through, right? So this is the difference between FN tunneling and the direct tunneling. And you see this in all the flash memory. Right? People will talk about direct tunneling and FN tunneling. If you plan to apply a job in Western Digital, in Samsung, in Micron, you better know what they are. Of course, you're circuit design, but still they might ask you, do you know about direct tunneling and FN? But if you say I studied the device physics, 2 classes or whatever, and you still don't know this, then they will challenge you, right? If you did not study, that is normal. Okay. Now, then filament, we have conductive bridge, which I'm going to discuss later in one slide, and oxygen vacancy. That is what we discussed, right? So here we have the hopping from trap to trap, right? We also have so-called Pufenko emission. This one I did not cover. Space charge limited current, I did not cover. Ohmic conduction, just a regular conduction. Trap assisted tunneling. This one I kind of cover a little bit, right? So we have different mechanisms, right? Here just to show you that, hey, we spent so much time, we still did not learn much. Indeed, that is true, right? But just know what is the background. All this you just Google, type this keyword and then type wiki, W-I-K-I. It gives you everything that you need, right? You don't need to memorize, but just know that you have this, okay? Any questions about this? If not, I want to talk about this so-called conductive bridge RAM. Sometimes people confuse it with resistive RAM. I don't think there's any, like, it's not a law, right? This is not definition. We don't need to be too care about this. But the most important thing is about communication. What do you mean when you discuss CBRAM, conductive bridge memory, with me, right? So you want to confirm with your other people to make sure that you are on the same page. So be careful about this, right? So what is this? It's also nothing fancy. It is basically, it's just electrolyte. We have, and of course, this is a solid. You can say this is solid electrolyte. If any of you have learned about the solid battery, right? Lithium battery, right? Some of you, I think some of you came from the material department, or I forgot. You know better than me. I'm not good in this area, but basically it's just electrolyte. So what happened? Let's look at an example, right? So this is, we call it anode, right? What does anode do? when anode, we applied positive bias to it, right? Then what will happen? It's going to take away the electron, right? So it is called oxidation, right? It do the oxidation, right? Take away the electron, right? So here, because of this, then you have all the copper ion here will deposit in this side, right? You take away the electron, and then the copper ion is going to be, these are the copper ion, right? Then they are going to be attracted to the cathode. Then they deposit there, and cathode supply electron. Then what happened? They become copper again, right? So if you keep doing this, eventually you form a filament of the copper filament, right? I just put here. Maybe let me just highlight it, right? Filament, okay? Bridging the electrolyte. Then it becomes conductive, isn't that? And this is still a filament conduction. But last time when we talked about oxygen vacancy, is the vacancy let electron to hop. But here you really form the metal bridge. Then it becomes conductive. And if you apply the opposite direction, then you have the reduction reaction. Reduction means I take away the electron again. And then your copper becomes this is Cu2 plus. Then you, what we call it, dissolution of the filament. And that is how you form the so-called conductive bridge RAM. And you see that it is as simple as resistive memory. So you can put in the same architecture. Is there any questions?
So I guess here the source of the bridge is the anode, whereas in the resistive RAM, the source of the bridge is the material in the middle via the holes.
You can say that, yeah. But you know, sometimes it's very difficult to distinguish because this is a copper ion and this is a copper atom. So which one is which when you do this exchange? But yeah, you can say the source come from here. Yeah, if you talk about, yes, but think about, yeah, okay. If you want to say, okay, the source of the bridge is because it's the copper, yes, it comes from the anode. And then in resistive memory, the source of the bridge is the vacancy. Yes, the vacancy, you can say come from the oxide, but remember, vacancy is nothing, right? The oxygen come from the oxide. So I will claim that the vacancy come from the anode. Just a little bit philosophical question. Of course, there may be rigorous solid state physics that can say that vacancy come from the anode. But what you're saying is great because it point out that you understand what's going on. It doesn't matter whether we want it to call it the source is from the oxide or from the metal. Very confusing. Do you see what I'm trying to say? Do you agree? Yeah, but I mean, you tell the correct physics, right? But what is the source, right? Now vacancy is conducting, so I will claim vacancy come from the metal, not from the here. Okay, but this is just for fun. Yeah, good, right? So good. You understand everything. Now here, just to show periodic